So again, the topic here is to try and make life easier. We're going to look for some patterns and try and figure out how we can make these derivatives happen without the limits. Now know that once we do have these patterns, they would never be accepted unless we went back and did them with the limits to prove they were true. We don't need to do that here because I'm just going to, you can accept what we're about to go through is true. But know that, those shortcuts only exist because somebody had to suffer through those limits. Okay, here's a constant, y equals 2. And of course, it's too small. Here's a constant. What do you think the derivative is? Okay, good, 0. What if I do like y equals 1? Okay, here, hang on. Let me see if I can come up with a tricky one.
0, 3.
Oh, okay, one more. Ready? How about pi? Y equals pi. Oh, you guys, okay. So, what do you think the derivative of a constant is? Okay, so here's a notation that we're going to use today. This is the derivative of a constant. Oops. Equals 0. And this is from the Leibniz notation that we briefly mentioned earlier. So our first rule is the derivative of a constant is 0. Now, I'm going to give you these derivatives, and I want you to see if you can spot some patterns here for me. First of all, this would have a derivative. F prime of x is equal to 5. G prime of x in this case would be 6x. And h prime of x would be 3x squared. So what I want you to do is think about what the pattern is here, and if you're right, it works for all three. So take a minute and think about it. Okay, that's right. If you didn't see it, I didn't think it would happen that quickly, but you put the exponent to the front. So the exponent here was 1. Exponent goes to the front, so 1 times 5 is 5. Subtract 1 is 0. So yeah, I could have written x to the 0, but of course that's just a 1. So that's why we don't have it there. So yes, that's correct. And we'll check to see that the pattern is still working. 2 times 3 gives me the 6. And then I subtract 1 from the exponent. And yep, that's working. So far it looks like the pattern is still correct. Move to the front, subtract 1, still works. So here's the power rule for derivatives. So if you want the derivative of something like this, it's going to be n times x to the n minus 1. So the first one should be fairly easy. What would the derivative be of 7x to the 6th? Yeah, 42x to the 5. The next one is a little trickier. Anybody have a suggestion to help us out? Rewrite it, yeah. So if we want to rewrite this one, how would you write that? It would be an exponent. Do you know what the exponent would be?
3 over 2.
Yeah. So 3 over 2 is the exponent. I always remember that if I forget, the roots are on the bottom like a tree. So roots are underneath like a tree. So now if I do the derivative rule, the power rule, it's going to be 3/2 x. Subtract 1, what will I get? Yeah, 1/2. So you could write this as well as 3 root x. 3/2 times root x. Okay, what about the last one? What do you think? Hold on. What do you think? Look at what I wrote up on the board. What do you think?
The same thing.
I'm just asking you. Do you think that's legit?
Nope.
No, yeah. That's why we're doing this one, to illustrate to you. Sometimes you're in the power rule and you just start cranking out answers, not thinking about what you're doing, and that's one of the cases where it doesn't work like that. It's definitely not just take the bottom piece, because that's not the function. The function is this whole fraction, so we have to consider the whole fraction when we do it. So what I'm going to do is rewrite this as 1/2 x to the negative 4. Okay. So now it's easy for me to see it and use the power rule to find the derivative. So the derivative, if I multiply the front, it's going to be negative 4 times 1/2, and subtract 1 is now at negative 5. So it'll be negative 2x to the 5th. And of course, you may also want to write that as 2 over x to the 5th. Either would be fine. Sorry, negative 2. Negative 2. All right, so my tip for you is, if you can't see it right away or you're not 100% sure, try rewriting it. In this case, it's going to help if you use parentheses or brackets. So give them a try and see if you can come up and agree with your neighbor on what those derivatives should be. Yes, there is a negative missing on this one. Okay, so hopefully we're on the same page. It is possible that I've made a careless mistake somewhere. I have been known to do that occasionally. Oh good, no one laughed that time. The first one, basically all I'm saying is if you try and get the exponent all by itself, it helps kind of clarify what you're doing. This is the only thing you have to apply the power rule on. So by putting it by itself like that, I can then rewrite it. So negative 3 would be multiplied and subtract 1. Again, if you put it by itself, you're only thinking about applying the power rule. You don't have to worry about those coefficients. So 14 over 3x. And then, is that correct, the last one? Did anyone else get 126x? We're not there yet? Okay, perhaps I went a little fast through those 3 examples. But I think they're both correct. I'll just give you a minute to catch up if you're not there. All right, so let's go over the last set of, I guess, laws or theorems for the day. The constant multiple, if you have a derivative like this, which is some constant times a function, it's the same thing as the constant times the derivative of that function. So we can pull a constant out. Whenever you're dealing with a constant, you're fine to factor it out and do all the work without it there to annoy you. That's what we did in these last examples here with those constants. We actually had to apply that rule. The sum and difference, if you want the derivative of some pieces that are added together, so if you have f of x plus or minus g of x, that would be the same as taking the 2 pieces apart. So take one derivative, and you can plus or minus the other derivative. So now we don't need to just work on monomials, we can also work on polynomials, and we can work on anything actually with an exponent, now that we have this power rule and these constants, sum and difference. How would you prove these? You can do that using the limit definitions we did before. Now one thing that's going to surprise some of you, it seems obvious, like why would we do this? This is just to confirm that yes, what you would expect to be true is in fact true. It's not always going to be the case. There are a couple of funny rules when it comes to derivatives. But these ones, yes, you can safely assume that what you would, your thoughts on it are actually true. Adding and subtracting, you can split them apart, and the constant can be taken out. Okay, so this is one where things have been added together, and there's constants, all that other kind of stuff. So what do you think? What would the first derivative be if I'm working on this one? You guys want to use limits? No? Okay. What do you get? X cubed minus 4x plus 5. Use a shortcut. 15x is a little large. All you have to do is think about each piece. So that's what we just worked out here. So what's 3x squared? Or sorry, I just said it. X cubed becomes 3x squared minus 4. And that 5, the derivative of a constant, is 0. So that used all the rules we've practiced so far. 3x squared minus 4. Okay, what about the derivative for g here? Oh, it's not that bad. Come on. You want to use limits instead? Yes? Okay, so I know they're brand new to you. Why don't we take a look at the first piece one at a time? Negative x to the 4 over 2. What's that derivative going to be? X cubed, yeah. And then the next piece? Good, 9x squared and minus 2. So we can really quickly piece together those derivatives then, knowing that those rules apply. So here's the first couple. I'm going to prove one of them to you, but the derivative for the sine of x, it's kind of surprising, but maybe not. It's the cosine of x. And the derivative of the cosine of x, what do you think it is? Oh, so close. It's the negative sign. So I'm going to prove one of them to you to give you an idea of how we actually come up with these rules and know that they're true. We have all the skills to do it. It's just really, you're not familiar with this idea of proof. So basically, when I do calculus, proof is something you're going to run into next year. I pick the simplest proofs to walk you through, just so you get some exposure to how they work. So this one here is not so bad if we use the definition of derivative. So the limit as delta x goes to 0 so I'm taking the derivative of sine. It's going to be sine x plus delta x minus sine x. And I divide that all by delta x. Now, do you remember something from Math 12? So forget about your calculus for a second. What could you do if we were just to look at this, cover up the calculus for a second? What could you do if this was like a trig identity? Well, we can't factor out sine x because it's not quite. Yeah, we're going to use that identity that we learned, right? So we learned about this identity, which maybe it'll jog your memory once you see me. Sine x cosine delta x plus sine delta x cosine x minus the sine of x. So maybe that's familiar, maybe not. But now what I'm going to do is I'm going to rearrange it for you. This is, that's kind of not so surprising that we're going to do that. But the next part takes us, I don't want to say stroke of genius, but it does. That's the hints that I've given here if you wanted to try it on your own. You're going to rearrange it to use a couple of the limits we've already found with trig. So I'm going to rearrange it like this so you can see how this falls into becoming the cosine. This will be sine x cos delta x. And I'm going to move this piece over because now I can do some factoring. And this will be sine delta x cos x. So here's what it's going to look like now with the two pieces. This is a fraction. I'm going to split this fraction into, hit the space bar. Delta x goes to 0, and I'm going to split this into two pieces. So the first piece is going to be sine of x cosine delta x minus sine of x. And then I'm going to add the second piece to it. So this will be sine of delta x cosine of x over delta x. So at this point, those of you who are really comfortable should be able to finish this off without my help. I'm going to give you one more step and see if you can then figure out how this would work. Sine of x times 1 minus cosine delta. Oops, sorry. Yeah, I'm missing that piece. My apologies. I'll factor that out. So at this point, you should recognize one of the limits I just wrote down. And you should recognize this limit as well. Yes?
Does the limit still apply?
Yeah, of course. Of course, yeah. So what do you recognize here? What's one of the limits you recognize?
1 minus cos x over x.
Yeah, so here's one of the limits that hopefully you haven't forgotten about just yet. But that limit there equals 0. So that means this whole thing is gone. It would be 0 negative sine x times 0. So whatever might have come out of this is gone because I just multiplied it by 0. Sine of x has no problems, right? I'm not worried about sine of x, but whatever number it is, it's just multiplied itself by 0. Over here, sine delta x over delta x as x goes to 0. Yeah, that's 1. So if that goes to 1, I have the limit as delta x. I swear I must have magnetic hands or something. I don't know why it does this. Of just cosine of x. And now you let delta x go to 0. It's not even in the problem anymore, so it's just cos x. So that's what's left over once we go through it using definition of derivative. So again, it's not that it wasn't important that I teach you the definition of derivative. It's used all over the place, but our focus is now going to leave using definition and going towards the consequences of that definition, right? Like one of the things we get out of it is this derivative here. Now, before we go any further, take a deep breath. No formula sheet for AP Calculus. However, everything you need to know is on one page on the inside cover of your textbook. So that's it for the whole year. And I'll tell you right away, it's giving you 2 sets of rules. You're going to learn that you really only need to know half of them. So you really only need to know half of that page, but there is no formula sheet for that half a page. I know. The reason I'm telling you is these are 2 of the things which normally you might think of on a formula sheet. No, you got to know them. You have to know those 2 derivatives. Okay? Okay, so let's put them together then. If the derivative was 2 sine x, if the function was 2 sine x, what's the derivative?
2 cos x.
Good, 2 cos x. All right, sine x over 2 is cos x over 2. And then x plus cos x. What will it be? X plus cos x?
1 minus sine x.
1 minus sine x, good. Okay, so the derivative of x is 1, and cos x is negative sine. Trust me, I don't know anyone who ever forgets those. You know, once we get another week into this, they're all over the place. We'll be practicing it all the time. So even though it's something you're going to have to remember right now, it's going to be very easy to commit it to memory. Now, this is about to become your favorite function. You remember that natural log and natural exponents? Well, the derivative of the exponential natural exponent is just the natural exponent. So that's a weird graph. It's a graph where the value at every point is equal to the value of its tangent line. So it's got a kind of a nice property, and that's something that we'll see later is also, there's more properties of that graph which are really special too. So let's put them all together then. All the rules we've done for today. What will the derivative here be?
Same thing.
Yeah, it's exactly the same, 3e to the x. Remember, you only have to consider, the constant doesn't affect it. You only have to consider e to the x, which is your favorite derivative because it's e to the x. If they were all that nicely behaved, you wouldn't need to go to calculus class, right? Okay, what's the derivative for g?
2x plus dx.
Should we do the last one with limits just for... No? No? Okay. Yeah, I don't want to either. Okay, so what do we have then on the last one?
Plus x minus dx.
Good. So again, this fact here is one which you must know, but I'm telling you it will be very easy to commit to memory. You're going to see it for the rest of the course. So here's a couple things that we'll take a look at. Average velocity, that's just like your regular secant line or your grade 10 slope. So you could do that as like, we'll call that, you take your velocity at time t minus your velocity at time 0 divided by t minus 0. So if you have a billiard ball and you drop it from a height of 100, I'm going to guess feet here, that'd be fun to do, wouldn't it? That'd bounce, or I'd probably shatter when it hit the ground. But anyways, I believe this is actually the model that it would produce in physics. So those of you who are doing projectiles and stuff like that, you're going to get some formulas in physics that you'll see in this class too. But what's the average speed if we wanted to figure out as it goes from time 1 to time 2? Well, average speed is just that slope you knew before. Average speed is the average rate of change. So let's find out what's the, oh yeah, sorry, this would be, I guess that would be average velocity. My apologies, that should be distance. I guess I got too excited about the physics there. So this would be the height at time 1 minus, sorry, the height at time 2 minus the height at time 1 over time 2 minus time 1. So if we were to look at that ball falling, here's 100 feet, and the ball is like that, falling down, then we would take its height at those two times, and we would measure out what was the rate of change there. That'll give us the average rate of change for that ball. So this will be negative 16 times 2 squared plus 100 minus negative 16 times 1 squared plus 100. And it happens over 1 second. So first of all, those hundreds are going to disappear. I might as well just ignore them. I don't have to calculate those. 4 times 16, that's 64. And that's just going to be 16. So overall then, I should have negative 48. Why is it negative 48? Yeah, so for you people who aren't in physics, when things are falling or going down, it'd be negative, just like a negative slope. Like you see how this slope is going down here? It's negative because the slope is falling. So you should expect the speed to be negative too, or you've probably made a mistake, right? If it was positive, that means the ball is actually rising away from the earth. So that's average speed. That's the world you came from. But this is now what we can do with calculus here. So a diver jumps off the 32-foot high platform. So for us in Canada, that is a 10-meter diving board, the regulation one. Anyone jumped off a 10-meter platform? They have it at like Canada Games Pool and probably a few others. So we can actually figure out how fast you're going, assuming there's no wind resistance, right, when you hit the water. Because we want to know, I don't want to know the average speed you went. I want to know how fast are you going the second you hit the water. So first we need to know when do you hit the water, or I won't be able to tell you at that instant. So how could we solve that? What's the height when you hit the water? Yeah. Okay. So that means I'm going to take out a 16 here. Now, clearly the diver did not jump off at time minus or hit the water at -1, right? We're ignoring time before the time right now. It would be 2 seconds after he left the platform. Okay, so you're falling for 2 seconds, and what's the velocity when you hit? Well, remember, if we think about a tangent line as that rate of change at an instant, that's what we need to find is a derivative to tell us that rate of change at an instant. So what's the derivative of the height? Oh, come on, this shouldn't scare you now, right? What's the derivative of the height?
32, negative 32.
Yep, plus 16. Okay, so if we want to know negative 32t plus 16, I want to know what's the derivative at 2. Should I expect this number to be positive or negative when I'm done? Right, because I'm falling. So negative 64 plus 16. So this is going to be negative 48. And again, if we're dealing with feet, we'll be talking about feet per second. My units here are in seconds and feet, so the rate of change would be the number of feet per second. So 48 feet per second is how fast you're falling. You can go and convert that to miles an hour or whatever if you really want to know, but you couldn't answer this problem without calculus. So here's my challenge to you then. You're on the 10th floor, which we'll assume is 100 feet high, and you know this urban myth where like, oh, you're fine, all you got to do, if the elevator's falling, yeah, jump at the bottom, right? So there might be some truth to that, but if you know the physics, right, you're thinking, I have to jump as fast as the elevator is falling so that those two forces cancel out, right? That way the net effect would be velocity 0. You'll be safe if you can do that. So what I'm saying is, if you know how fast the elevator is hitting the ground, like let's say it's 10 kilometers an hour, you have to jump up with a speed of 10 kilometers an hour. So let's just say it's a 10th floor. You find out how fast do you have to be able to jump up off the ground at that instant to actually save yourself. Is it possible?
Height is 0, so find how long it takes.
Oh, it's the only way. Oh, just put 100 over 4.5.
Okay, so 44.3 feet per second. So again, that's pretty fast. I mean, let's go and ask an expert here. Google knows everything, right? Convert 44 feet per second to miles per hour. Man, it's smart. Look at that. So you have to be able to jump 30 miles an hour, which is 50 kilometers an hour. So you know how fast the cars go by at 152nd Street right there? That's 50 kilometer hour zone. So try and jump as fast as the car is going as you're walking along the sidewalk next to it, right? See if you can. You won't. I don't think you can. Easy? Super Tony? Okay. Anyways, so hopefully that gives you some more, a reason to hope that this class won't be so brutal as it just was with limits. Again, I apologize for having to put you through it, but this is where we're going now, is to use those limits to make life easier. So you can get started here with your work on derivative rules.